Okay, this is lab number 2 for week number 2 in the computer-aided engineering course. And on the agenda, I have several items today. And first, I'm going to solve the problem chapter 8, which was actually already done earlier, but using tetrahedral elements, where I had a C-clamp under enforced displacement. And then after I do that, I come back and go through an item that we didn't have time to finish last time, and that is called imposing a load at a point. So we'll see how what that thing means. In order to do that, you have to be in the advanced meshing tool, advanced meshing tool, not ATM, AMD actually, advanced meshing tool. All right. And then finally, I'm going to do a problem from a previous exam where we're going to use the local 1D property in order to change the cross section of a beam from one part of the model to the other part. Let's not worry about it right now. So the first problem I'm going to do is right here. You have already seen it on the right-hand side. And we're going to do that with beam elements. Now, if you're going to approximate this thing with beam problem, we cannot model that hole anymore. So essentially, we have a clamp, a C clamp without that hole, but we're going to model it with beam elements. This beam wireframe, the wireframe of this is actually a planar curve, and therefore I can draw this thing both in the space and as a 3D curve, or I can do it in a sketch, which is another alternative. So I'm going to do it as a sketch, okay? Because the example problem from previous midterm is something that cannot be done in sketch. And then, of course, there you're going to see what the process is. Okay, so let me go ahead and create a model. Start with a part file. Immediately save this thing, file, save management, save as. Okay, so I'm going to go up, desktop, in my desktop, new folder, and I will call this thing C-clamp with beam elements. Okay, so everything is going to go there. Now notice that right now I am in wireframe and surface design. At some point, if you're going to do beam problem, you have to come to this workbench. You have to come back to this workbench because you're going to need the join icon here. That being the case, I will stay there instead of going to the part design and then create my wireframe in a sketch and then come back here and then join it. I'll do it just right here. So on that vertical plane, I will sketch. By the way, in this particular problem, the way it's stated, I do not have a symmetry along the horizontal line. If, on the other hand, I clamp the top, sorry, if I took these the top and the bottom and pushed them away from each other, each by 0.01 inch or 0.001 inch, then this will be a planar symmetry. But the present problem, I don't have that because I'm clamping this point and I'm applying a downward displacement. These are not the same thing if this is clamped and this is pushed down. But if these two were pushed away from each other by 0.001, then this would be a planar symmetry, and I will need half of this. Okay, I will have to model half of it because all my problems say use as many planes of symmetry as are applicable, but in the present problem, I don't have any planes of symmetry. Okay, so let's go back here. I'm going to create my C-clamp. We'll put dimensions in a minute, something like that. and we're going to use the dimensions that are given. I believe that this is 2 inches, and this is 2 inches, and this radius happens to be, based on the drawing, happens to be 1. Good. Now, if you insist that this be exactly halfway between these two, which is actually unnecessary, but if you insist, then you can move this whole thing. You can move these things. You can move it and then symmetrically place it. It is unnecessary, but I'll just leave it like this. Okay? Exit. There we are. Let me remind you that we're going to have to join this. By the way, the cross section, notice that the cross section is not a circle. So I need an orientation point. So let me go back here and uh, let me, I mean, if that is the case, it is actually better if I either put this thing on that axis or actually make the axis be exactly halfway between these two. It's probably that's fine. I select this, control that, and I make him coincident so that later on when I want to create the point, I know exactly what the coordinate of it should be. There. Very good. Exit. All right, did we join this? Let's make sure. No, I haven't joined it yet. Let me also create my point. You don't have to create a point right now, but let's do that anyway. So I'm going to create a point, and now I know that the height of this, the z of it is 0, but for x and y, I can use anything except that z is 0. So z, for example, I'll make maybe I make 1, or let's make it 2 and 2. Actually, that's fine. That'll do it. Okay, good. Um, Let me also move this thing a little bit to the back, although this probably would be okay. So -3. I don't think that's necessary, but that's fine. I'm gonna find there. So I created a point which is not on that line because the orientation point cannot be on the curve itself or on the continuation of the curve. So what I did is I actually made it away from the curve by some distance. Good. Now we're going to join this, and all we need is select that, so it's automatically joined. Without this, we cannot apply, we cannot, later on, we cannot apply 1D property itself. So we joined it. And we're going to make it out of steel, for example. So default properties, there we are. And let's save this thing. So file, I think we already saved it. So let me click on the floppy so that it saves whatever I've not done. So now we're going to go to start, analysis and simulation, generative structure analysis, static analysis. We're going to do beam problem, beam elements right there. You see this beam? Select that. And what do we make the element size? Because this was 2 and this radius was 1. That's too big. So let me make it point maybe 1. And then we say, okay, let's check it out. Right click mesh visualization. There we are. And if you go and you see that there are elements and node numbers here, you can see that. For example, this one is element 43, node 45, and 46. You can see that. Good. So the rest of this is deactivating that. Very good. Now we do 1D property. There is the, sorry, not, yeah, 1D property. You click on this. See that? 1D property. You click on it. And the support is that joint that we selected, but the cross section is not circular, it is actually rectangular, and the size of it, you click on the range, and the size of it based on the statement of the problem is 1 by 1, I believe. Okay, so let's make sure that it was 1 by 1. the cross section. I am pretty sure it was, yeah, 1 by 1. This is a 1 by 1 square cross section. Now, the only issue is that this is kind of randomly oriented in space. Okay, so what we need to do is that, first of all, we cannot close this because the cross section is not a circle and we have not selected the orientation point. So I click on the orientation geometry here, and I select this point. Look at what happened to those red cross section there. And well, that is not good. Okay. So what I'm going to do? I'm going to change the coordinate of this thing. Cancel that. The coordinate of this, I have to move it to a different point so that it gives me what I want. Cancel that. Sorry. So let me go to this point, and let me actually do the following. First of all, for Y, I do for Z. For Z, I will make. I want to move this thing up there. So maybe for Z, I make uh, 1. Let's see how it looks like. There we are. And for X, I will make 0. Okay. So it's right there. Now we go back to the analysis and create the 1D property. Let's try it again. Click on 1D property, select the support, change the section to rectangular, and for the size is going to be 1 by 1. We already agreed on that. Now for orientation point, look at what it is now. But for orientation point, let me select this point and look at what happened. There, that's exactly what we want. The cross section square here, perpendicular to that, perpendicular to this, and perpendicular to that. So I told you that this orientation point is critical, and it's not really a trial and error, but if you want me, come and ask me a little bit more information about uh, what the trick is, and it's not the trick, a little bit more about the nature of this point so that you get what you want. If the cross section is circular or hollow tube, okay, it makes no difference. You don't even need the orientation point, but we say okay. Very good. All right, let's save our analysis. So file, save management, analysis, save as. Is this the folder? Yeah, C clamp with beam elements. That's where it goes. All right. So what do we know? First of all, this top point is clamped. And the bottom point, we want to push it down by 0.001 inch, right? 0.01 inch, sorry. So remember that in order to specify a non-zero displacement in CATIA, unfortunately, first you have to make it zero displacement. How do I make a zero displacement? User define. Let me uncheck all of these things. This thing, first we push it down by 0 amount. That's this. And now we can go and click on enforce displacement in the load section. Enforce displacement. You select this and you can change it to negative 0.01. And we say, okay. So notice that here's the situation. The restraint, we had clamp and user define. And the reason we did user define because we wanted to make this thing 0 so that we can go later to the load and change it. Okay. Very good. So save it and run it. Let's click on the compute calculator. All right. This is going to go down. It should go down, otherwise there's something wrong. Let's try it. Here we are. Double click on this average horizontal. That's the way it should be, right? So if you look at the view from the side, let's look at this side. Good. And this point is clamped. This one is being pushed down by some amount. If you don't want these properties and they're bothering you, you can hide them. There we are. You can see that. And you can animate, of course. There we are. If this is clamp and you're pushing down, this is going to go down. Now the question is how much force is needed to do that. It's the same story as before. So you go to sensors, right click at the very bottom, not the very bottom, but second last. Uh, it says create resultant sensor. You go to reaction sensor, you click on it, and it's going to ask you where is the entity that you want to find the force at. Well, you can select either this or the clamp, it doesn't matter, but let's select the place where that we actually applied the load, right here, right there. You see that here on this, and then you say straight, and you're going to get 800 and what is that? 837 pounds. 837 pounds. Okay. Uh, yeah, that's pretty much it. So this is the amount of the force that is needed to push this thing down by 0.01 inch. We say okay. Don't say cancel, because if you say cancel, there is no record of that in your tree, and I don't know where you got your number. But here, if I double click on this thing, I can see exactly what it is after you uploaded your work, if this was a test problem, etc. And you're pretty much done. So you repeat that problem using beam element. Now notice that the only issue is that we cannot plot von Mises stress in beams. Okay, you can plot the principal stresses, but that's totally useless. Okay, so there. All right, let me close this and close that and go back here. Okay, so if incidentally I had solved that problem, but the only difference is that we were pushing this point up and pushing this point down by 0.01 inch, then xy would be a plane of symmetry, and you model only half of this. See that? Only half of this. You model only half of this, or either the top or the bottom. And because xy is a plane of symmetry, then you use conditions at that cut like that. Which cut am I talking about? If you use half of it, this is the point that you cut it right there. And if xy is a plane of symmetry, you say translation in direction xyz. Let me see now. You're cutting it with the xy plane. So displacement in the z direction is 0, and these are free. And exactly the opposite for the rotation. So if this is 0, this is free. These two are free. These two must be 0. Okay. So what I want to do is now show you uh, a problem from a previous midterm or previous test. Let's put it that way. And just give me a minute. Okay, the problem that you want to do now is a beam problem. And let me first show you the geometry. So we have this geometry displayed to you on your exam paper like that. And you're asked to use the most appropriate element. You should not be using the solid elements here. You have to use beam elements, otherwise, you will lose some marks. In fact, you have to use beam elements. As simple as that. Okay. Now, and this was mentioned. This was mentioned in the in class that you need to do this thing with beam elements. Okay. All right. This is just a rough idea to give you a rough idea how these things work as far as the choice of the elements and things like that. Now, uh, these ends are clamped, and here we are applying let me see now, we are applying a force and a moment. Let's read this problem carefully. It says that the ends are clamped, and a concentrated force and a concentrated moment are applied at the exact halfway point between D and E. At this point, exact halfway point between D and E. The magnitude of the displacement is 0.001 inch, and the magnitude of the twisting angle is 2 degrees, okay, about the y-axis. You have to model it, and you have to tell me in here what is the twisting moment needed in order to cause this deformation. Okay, use all planes of symmetry, if any. Use the most appropriate element. First of all, you know that you have to use beam element. Simple as that. And as far as symmetry goes, just think about what I just told you. Obviously, this vertical plane, xz plane, is a plane of symmetry. So you need to model only half of this. Okay. All you need to do is to get the coordinates A, B, C, D, and halfway point here. Okay. So A here. Let me see. A, B, C, D. A, B, C, D, and halfway point. Or you can do H, G, F, E, and halfway point. Okay? So let's go ahead and first of all create these points. The coordinates are given here for your information. The halfway points, obviously, between D and E. If you look at the D and E, you take the halfway point. It's going to give you uh, uh, the coordinate here is -5. This is -5, and then uh, yeah, this z is -5, and the y coordinate is uh the y coordinate is 0, and the x coordinate is 5. Okay, so 5 and -5. Okay, just take the d and e and take the average of the two. You get 5 and -5. Okay, and 0. 5 -5. Okay, so let's go ahead and do that. I'm going to go to, just remember these numbers you have to, these coordinates you need. Okay, so let's go to here. Start with the part file. You can do it other ways too, but this is how I'm going to do that. All right, so let me create a bunch of points. First of all, save this thing. File, save management, save as. Let me go one level up and create a new folder. So previous midterm, all right, and then we say okay, open. All right, let's create the points. So where's the icon for points? Right here. Double click on it. Let's do point A, and I'm going to coordinates. I'm going to type in the coordinates because I already gave you. Point A has coordinates 0, -10, and 0. So this is -10. Okay. Point B, shift this thing. Okay. Point B has coordinates 0, -5, 0. So this is going to be -5. Okay. Point C is going to be 5 -5, 0. So this is going to be 5. All right. And point D is 5 -5 -10. This is the point D. And the halfway point, we just said that it was halfway between D and E. Take the average of the two. 5 minus 5, 0 minus 5. 5, 0 minus 5. There. Cancel. So let me see now. Did we get all of them? I think we have one problem there. I think this is a mistake. This should be, coordinate should be -10 actually. There. Now we're going to make lines. And how do I make the lines? The line between this point and this point. Okay, another line between this point and that point. Line between this and this. All right, and finally between these two. Good. So this is what you got. And what you see there is actually A, B, C, D up to a halfway point. Very good. Now, join these. Don't forget to join. Here's click. You don't need an orientation point because the cross sections of both pieces, which are different by the way, both or circles. Okay, so I'm going to join this and that and that and that, and then we say okay. So it's already joined. These points, I don't need it. I can always hide them. In fact, it's a good idea to hide them because you don't want to accidentally put a force or a restraint on a point. Or you want to put it at the ends of these vertices, okay? So now we already joined it, we apply material. I think the properties are you're asked to use steel default properties. So let's see now, yeah, steel with nominal, yeah, uh, steel default. Okay, so let's go ahead and do that. So metal, steel on the part, and then we say, very good. That takes care of this. So save everything. Now we're going to go to analysis and simulation, generative structure analysis. It's a static problem. Okay. We're going to measure it with beam element. You click on the beam measure because you joined everything. Everything is going to be selected at the same time. Well, why don't we make this thing maybe 0.5? I don't think I gave any instructions on that, so you can select it yourself, and then you can look at it if you want. Right click mesh visualization. Okay, you can see that the elements are created here, and there are no duplicate nodes because you actually joined these things. So let's deactivate them. Now the big question is this. In the past, every problem that we had the same cross section, but here the cross section of these vertical member on the right side, these things, is bigger than those. So what we have to do in a situation like this, because of the one way of doing it, because of the approach that I'm taking, first thing you're going to do, you're going to make everything. For example, everything means A, B, B, C, C, D, D to the middle point that we created. We're going to make a circular cross section of radius, say the smaller one. What do we have here? Let's check it out. The smaller one, let's see now. Yeah, the smaller one is radius 0.15 inches. And then we're going to change the one for these middle ones. So let's go here. 1D property, circular, cylindrical. You click on it, 0.15, 0.15. You say okay, and you select everything. So it's going to put 0.15 on everything. You can see that right there. You see this? Everything is 0.15, including these. But that's not correct because I know that these two have to be radius of 0.4. All right, so how do we do that? You go to the properties in the tree. See that? You go to properties, put the cursor on the properties, right click, you go down, local 1D property. It says, okay, you want some of these not to be a certain radius, 0.15? You say, yes, so I want this guy and that guy to be cylindrical, but the radius of it, I want to be 0.4. And then I say, okay. And then I say, okay. Notice that what happened is that on this line and that line, it uses a bigger circle, but on the other one, it uses 0.15. Don't let this 0.15 bother you. It is actually 0.4. This is being replaced by that local 1D property that you did that. So this is the one way of handling the problem. And obviously, people were given, you know, good. For people who wrote the midterm that year with this problem, we had done other things which showed them how to do it. I didn't expect this thing to be discovered by them. Okay. Now let's save our analysis file. So we go File, Save Management, Analysis here. It has to be saved, Save As. This is the right folder. The previous midterm. Yep, good. And then we say OK. What else do we know? We know that this top point is clamped. Okay, good. We know that this point is a point of symmetry. Let me hide these properties here. Okay, we know that this is a plane of symmetry. Okay, this is in the XZ plane of symmetry, and we know what to do. So we go user define. This point because it is XZ plane of symmetry, no translation in Y, which means no translation in direction 2, rotation exactly the opposite. So this takes care of symmetry. Okay? So let me show you what happened. This first restraint shows symmetry. In fact, you may want to call this thing symmetry restraint, just so that you know what you have done. Symmetry restraint. Very good. Okay, good. Now, let me hide this also. Now, I want to push this thing down by some amount and rotate that by about this axis, about the axis Y by some amount. So what do? First, I do a user define on this point in the direction Z, and I will call this pushing down so that I know that this strain is actually from pushing down, and another one, and I'm going to call this thing twisting, about the y-axis, which is direction 2, not this, direction 2, right there. And this is the point right there. See that? Right there. You see this? About that, in the positive sense by 2 degrees later on. Now that we know that things have been applied for pushing down and twisting, I'll go to the enforced displacement, and you select, for example, pushing down by negative, what does it say here? Negative 0.001. So negative 0.001. Okay. And again, enforced displacement of twisting by 2 degrees. 2 degrees. That's what it said. Okay. Let's save this. Run it. Okay. So let's use it. Let's run it. Compute. Okay. Good. So look at the displacement. Let me change this thing to average ISO. Very good. So if you want to look at from side and animate it, what happened? It goes down. This point goes down, and this angle is being twisted by 2 degrees. So this is what you're going to get for example, motion. Now the question is how much moment do you need to twist this thing by 2 degrees? So you know what the routine is. You go to sensor, right click, you go to sensor, right click, go all the way to create resultant sensor and say reaction sensor. It says, okay, what do you want to know? Well, I want to know what the twisting value is. The twisting moment is. You select twisting and you say update and the moment tab, and there we are. So you have to give it a 14.36 Newton meter of twist. But first of all, my units are inches and stuff like that. So let me say, okay, well, I'm going to change my units. So let's go to tools, because you have to write something down in this box, right? In pound force inch, not in Newton meter. So you go to tools. I mean, obviously you can use your hand calculation to convert that, but that's crazy. Tools options, under parameter measures, under units. Let's get the moment, if we can find the moment here. If you're having a hard time, click on magnitude so that it sorts it out in alphabetical. Let's find the moment. There we are. Moment, I want to change that to pound inch and then say okay. Good. So now that we recorded that, double click and moment, 127 pound force inch. So in this box, you write double of 127. Don't write 127, you're going to lose moment because we're modeling only half of the structure. And for that half of the structure, I need that 127, whatever. I have to write here 127 times 2. Okay? So that takes care of this midterm problem. Okay, so the last thing that I want to do is this item, and it's going to be done very quickly. I said, what if you want a point that should be on my beam? Okay, I want to apply a force at a point on the beam. Okay, I'm going to show you how to do that. Okay, so the in order to discuss this with item number C, what I'm going to do is I'm going to create a cantilever beam. The cross section of it, it doesn't matter. Let me assume that it's a circle. Let's say a 10-inch long beam, cross section circle 1/2 inch, and one end of it is fixed. The other end, I want to put a force on it, but not at the tip. I want to put a force somewhere somewhere along the beam. Okay, is that clear? All right. Now, one option is to break the beam, the line into two pieces and solve the problem. Here's what I mean. Okay, so I'm going to do the problem two different ways. We go here. First of all, let's get rid of all of this. Start with the part fire. All right. And I'm going to create a line. For example, let's actually do the following. Let's do on that vertical plane. I'm going to draw a line like that. And on purpose, I'm going to break it up, another line from this point to that point. And let's dimension these things 5-inch and 5-inch. So this is going to be 5 inches. And the other one is going to be also 5 inches. Okay, good. Exit. Notice that this is now made of two lines, okay? And join it. Join that. Join it. Say okay. All right. Apply material to it. So let's make this thing out of steel, aluminum. It really doesn't matter. So let's go to analysis and simulation, generative structure analysis, static analysis. Let's mesh this whole thing with a 0.37 inch element each. You can look at it if you want. Right click mesh visualization. All right, good. Now 1D property, you select, well, first of all, deactivate that. A 1D property, you select this. And I put down a circle of radius 0.5. There we are. We can close this. All right. Very good. Now this end is clamped. And I can put a force on this point because I broke it down into really two pieces. If this was not broken down into two pieces, this is not what I could have done. Obviously, there's no issue with it. There's no issue with the tip. I didn't have to break it down. But if I want to put some point in the middle, somewhere not at the tip, but in the middle of this, I had to break it down. Okay? Now, we can run this thing and nothing fancy is going to happen. This is just going to bend down. Okay, it's just going to bend down, nothing fancy. Right there. We know that. Not a big deal. The only thing you have to realize is that, you know what, you better break this up into, if you want to put a load somewhere in the middle, not at the tip. Now, I want to repeat the same problem, except that I will not break this thing down into two pieces. So let me close that. Let me close this. go back to a part file, I'll repeat the same problem, except that that sketch, I'm not going to break it down into two pieces in the space or in the sketcher. On that plane, I will sketch. Here is my 10-inch long, okay. Let's actually dimension this thing, 10 inches, just like before, 10. Before I did it 5-inch and 5-inch, broke it down there, exit. All right. And what I'm going to do is I will create well, first of all, let me join this thing. I can join it and then do what I'm about to do, or you can do what I'm about to do and then join it. It really doesn't matter. It's entirely up to you. So let me do the following. Create a point on this curve by a distance of 5. So there is a point on that curve. There is a point on that curve. I did not break this curve into two pieces, but there is a point on that curve exactly halfway in the middle. Now let me join this thing. And as I said, it doesn't matter whether you join it. You did this or you created the point and then joined it. Okay, good. Let's apply material to it. Whatever it is, aluminum. Can't remember whether I use aluminum or steel, doesn't matter. And now we're going to go to generative structure analysis, but don't go there. Go to the advanced meshing tool. Okay, go to the advanced meshing tool. Now these icons we have never seen because, and toolbar we have never seen because we never went there. Here is the beam mesher. You select it. Notice that there's a little more here. It says, okay, first of all, you can tell me what to mesh right there. And then you can say, what is the element size? 0.37. But then there is an icon here. It says, hey, I want a point to be on that curve. Add isolated point. You click on it. You select that point. Lo and behold, you're going to have a node right there, and you can put a force on that, on that, on that, on that point. The only thing is that when I clicked on this thing, let's use a different tolerance. So I'll make a 0.0001. That is the point. Very small tolerance because it didn't like it when I put 0, and then I say okay. All right. When I didn't use tolerance 0, it just didn't like it. As simple as that. Now, I can assure you that there is going to be a node right there. That guaranteed. If you want to see how, let's go now to analysis simulation, generative structure analysis. In order to do this kind of a thing at an isolated point, you have to do it in the advanced meshing tool. Okay, now let's look at our mesh. Right click, mesh visualization. And I can assure you, at this place where I have that point, can I see the point for a second? Let me see if I can see that isolated point. Hide and show. Okay. And I don't want to see this join. I'm going to hide that. You see that? Guaranteed that right there, there's a node, 3. And on this side, same node. Okay. And now if I put a force on this point, it will accept it. Okay, so let's go ahead and do the rest of the problem. First of all, deactivate our mesh. All right, deactivate our mesh. Where is my part here? Okay, good. So clamp, or did I do the 1D property? Let's do the 1D property on that whole thing. Same radius, 0.5. Good. Just one of them, I hope. Yeah, good. And then clamp this end. And now put a force on that point. You see, it takes it. And then we say okay and run it. Okay, and then you can look at the deflection right there. I did not have to break up that piece, into that line into two pieces. Okay, Now, this kind of a thing that you do in advanced meshing tool can also be used for surfaces, okay? And we'll worry about this thing next week. All right, folks? Excellent. So here we talked about this. Imposing load at a point must be in ATM in order to be able to go that route. All right.